So I have provided the template for our second set of vocabulary. Please add these pages in so then you don't have to write all this down in your blank pages. You can insert a PDF into an existing note. And if you need me to show you how to do that, feel free to ask, okay? So we're going to start with domain, and we'll start with the definition. Now, the definition of domain is the set of all possible inputs. You can say that's the set of all x values that are used, or you might recall that was our independent variable. And on a graph, we are looking from left to right, the x values that were used. So then let's look at this little graph I've provided. So we're going to go from left to right. So from left to right, our leftmost value is 0. And then at 1, we have a hole. And then we jump over to 2, and then we stop at 3. So how do we account for that? Well, we're going to put a bracket on the 0. A hole gets a parenthesis. That union symbol says that it could be an x value from our first set or the x value from our second set. Our second set goes from 2 to 3. They both are colored in. This means every value between 2 or 3 was used, including 2 and 3. So let's find some algebraically. To find the domain of each of these, the first thing we want to recognize is that is a polynomial. There are no square roots. There are no negative exponents. There are no fractional exponents. So since that's a wonderful, great polynomial, the domain is all real numbers, which we designate as negative infinity to positive infinity. At times, if they ask for interval notation, just you're going to put in that. Always make sure to use a parenthesis on an infinity. If they ask for interval notation, sometimes they have the option that you can type out the words all reals, and that would be okay too. Now, for B, it's a fraction. Fractions, just take your denominator, set it equal to 0, solve for any values that are skipped. So x is not allowed to equal -1. But the graph would show up everywhere else. So the domain for this one means I have a piece on the left side of -1. I have a piece on the right side of -1. But you'll notice that I have parentheses on the -1 because I have skipped it. On our last one here, because it is a square root, just take the inside, set a greater than or equal to 0, and then just solve. So that's x is greater than or equal to 1. How do we denote that on a number line or in interval notation? I start at 1, it's included because of the equal to, and I can go on to infinity. So that's how you would deal with algebraic ones. There's not much else I'm going to give you right now as far as domain for an algebraic equation. A polynomial is all real numbers. A fraction, set the bottom equal to 0. That's what you skip. A square root, set the inside greater than or equal to 0. Solve that inequality. That is your domain. So that's the algebra of it. Now let's take a look at some graphical interpretations. This graph has stretched to the left and to the right as far as we want to go. I never have to lift my pencil. I go from left to right as far as I want. So that is a negative infinity, positive infinity, or all real numbers. You will also see me sometimes write this all real number symbol. So it's an R with like a double back to it. But this example here, you'll notice that we have skipped 1, and let's assume this is at 2, and we have skipped 2 for different reasons. One, there's an asymptote there. One, there is a hole there. But you can say, I'm fine on the left of 1, but I got to skip it. I am fine until I get to that hole of 2. Then I got to skip it, but then I can keep going. And then our last one is an example of a square root function that has been moved to the left 2. I've shown you that spot at -2 is colored in. So let's assume that our domain starts at -2, is included because of a bracket, and then goes to the right to infinity. So those would be the x values from here over. So that's your first vocabulary word in set 2, domain. Next word we're going to talk about is range. So first, let's go to the left corner. Let's go to the definition. So the range is the set of all output values, the set of the y values that we have used, the heights that we hit from the bottom of the graph to the top of the graph. So go from least to greatest, which would be bottom, lowest to highest. Now let's go in the right corner. In the right corner, I'll be putting what I think of as like graphical interpretation. The range are the y values we've used, so I use this little subscript notation to remind you of that. And we are thinking about the heights. So let's assume, so I just have the same graph that I did before, but let me mark this as 1, and let's assume that this is at the same height. Let's assume that that's 1, okay? And then let's go to 2. So the heights that we are using, we have values at 1, they're both colored in, and we can use every value up to 2. Let's assume that's 2. I know it's not exact, but let's assume that's 2. Here's the kicker, be careful. Even though we are missing the height of 2 on this one has taken over and covered that for us. So let's assume if those come with those nice whole numbers, that our range is from a height of 1 to a height of 2. Now I know they're not real good. I should have included some physical, like actual grid lines, but let's assume it goes from 1 to 2. Now, how do we find the range of an algebraic function? Well, we have to have the graph. So we would put into Desmos our first one here. That is a graph that looks like this. It hits perfectly at 0, 0. So the lowest point of this function is 0. It is an included point. I could plug 0 in and I get 0 out. And the highest I go to is infinity. So low to high is 0 included to infinity. Same thing with this one. You either have to know what the graph looks like or you have to put it into Desmos. It looks like this. So the range is exactly the range we saw in part A. I have 0, it is an included point. I go as high as I want. In C, there's this little gap down the center along the along our vertical axis. And then there's a piece here and a piece here. The range are the y values. So I have all the y values from negative infinity to almost 0, and then from 0 to infinity. We actually skip over 0. So the way we would write this one is that our range goes from negative infinity to 0, skips it, and keeps going. Now that is very common with a 1 over x type of equation, 1 over x, 1 over x plus 2, 1 over x minus 4. They're all going to have an asymptote at one point, and we designate that as, oh, here's a piece over on this or down here, and there's a piece up here. There's a separation between the pieces at 0. And then let's do one more little set of ranges. So our first one says, what is the range of this function? Well, how low does it go? How high does it go? Do we skip anything in between? Now, I don't care that these bumps come up and down because this is going to go as high as I want. This is going to go as low as I want. They're completely connected. I'm not going to miss any heights. So this is in all real numbers, or negative infinity to positive infinity. Now the next one, you might remember this is a similar graph we had for domain. You can see the first height we get to is almost but not quite 0. And then I can get as high as I want. Even though this height is missing over on the right, it is not missing over here. That height is accounted for somewhere. Remember, heights or y values might repeat or might show up in different locations. So this would be from 0. I don't include it because I'm not going to land there, and I can go as high as I want. And then there was this square root function that we used in domain. The lowest point is 0, and I can stand at that height, but I'm going to get as high as I need to. So that's some information about range. Next definition we're going to talk about is a function. So let's start with our definition in the top left corner. We've got two different ways we can say it. It's a rule that pairs each input x with exactly one output y. So on a graph, a function passes the vertical line test, which means that any vertical line I draw will only ever hit it at most once. So now let's go to the right corner, which are functions. If you have a graphical interpretation, just think, does it pass the vertical line test? And this one does. This is a function we're going to see. It's a type of cubic function, and this would be a yes, because those vertical lines hit it once. But this one is no, because we can see that a vertical line will hit it many times, or twice. Many vertical lines hit it twice. So this one's a no. Let's go in the bottom left corner, which are functions. A graphical interpretation is a really good way to tell if something's a function. If you put this into Desmos, it looks like this. That's a no. But this one goes, and it's a parabola going upward. That's a yes. And this is a horizontal line at 7. That's a yes. So those are algebraic type functions. So the graph can be very important. But all polynomials are functions. They should be y equals the polynomial because this x1 lays it on its side. And then this last corner is just about using a function to input values. So let's practice doing that. F of 0 means take out the input of x and put in a 0. So that would be 0 plus 0 minus 7, which is negative 7. If we plug in 1, we get 1 plus 2 minus 7, which is negative 4. If we plug in negative 1, we get 1 minus 2 minus 7, which is negative 8. So you can think of those as ordered pairs. Like this is the ordered pair 0, negative 7. I input 0, I get out negative 7. So think of a function as a input-output device. I input something, I get exactly one output. So that's functions. Now let's go to vertical intercept. For vertical intercepts, let's start with the definition. That is another way to describe the y-intercept. It's the point where you touch the y-axis. It is f of 0, so plug in 0, what do you get out? If I input 0, what is my output? It is commonly referred to as b. The y-intercept is the point 0b. Now let's jump over to the right corner. I've provided a graph. There's not much we have to say here except, this is the point we're talking about. Where does it cross the y-axis? So you can put yourself a little note. Where does it cross the y-axis? So in this particular one, I've labeled it as some value b. So how could we find that vertical intercept or the y-intercept algebraically? Well, we just have to input 0 and find out what we get. So it's a pretty straightforward process. There are some functions you can't put it in a 0 input. That just means that it doesn't hit the y-axis. Okay, but let's look at our first one here. If we plug in 0, we get 0 minus 3, which is negative 3. So the y-intercept is negative 3. The b is negative 3. If we input 0 to this one, we get the square root of 1, which is 1. So it hits the y-axis at a value or height of 1. And finally, our bottom one here, if I plug in 0, I get 1 over 1, or 1. It also hits the y-axis at 1. So algebraically, finding y-intercepts or vertical intercepts are very nice. Just plug in 0, you got it. If you know the graph, and they want you to find the vertical intercept, please make that a vertical intercept. You just have to find what height does it hit the y-axis. Let's assume that one hits at negative 1. So you can either write b as negative 1 or it is the point 0, negative 1. This is an example where the B does not exist. It doesn't hit the y-axis. It doesn't hit the y-axis. And there are graphs like that. You know, it really just depends upon the circumstance. And there's what we know about vertical intercepts. Now let's jump to horizontal intercepts. 2 more to go. Let's start with the definition. It is the point or points where you touch the x-axis. A function is allowed to have more than one of these. You can call them the x-intercepts, the roots, or the zeros. So this one, you have to set the function equals to 0, so the point will always be something comma 0. 2, 0, 5, 0, negative 1, 0. If it hits the x-axis, it might not hit the x-axis, but an x-intercept 0 or a root, all asking for the same exact thing. So know that language. Now let's look in the right corner. The x-intercepts are the 3 points we've seen here. I haven't given them values. I've just called them generic, kind of A1, A2, and A3. So those would be the points A1, 0, A2, 0, and A3, 0. So wherever it hits that x-axis is a horizontal intercept or an x-intercept. If you put a graph into Desmos, you can tap on those points. They will give you what those points are. Their exact point they'll tell you. If not, they'll roll out to maybe 4 decimal places, I believe, 4 or 5. Okay. So let's actually find the horizontal intercepts for the algebra, a graph of it. So let's do example in the left corner here. So all you're going to do is you're going to set the equation equal to 0. And then you're going to solve for x. So I set 4x minus 7 equal to 0. I get 4x equals 7, or x equals 7/4. So that means I hit the horizontal axis, or the x-intercept, or however you want to say it, at the point 7/4, 0. Now for b, it is a polynomial function in factored form, which is great because then we can set that equal to 0, and that allows us to set each piece equal to 0 and solve it. So this one's naturally solved. Don't forget that x is an important piece. This one, you move the 3, divide by 2. This one, you just get to move the 1. It becomes negative 1. So we end up there with 3 places that hits the x-axis or horizontal axis. So it has 3 horizontal intercepts, okay? And then here, let's assume I'm counting by ones. It says find the roots of the function. It's just these 3 points that we see here. So it would be a root at x is negative 2, negative 1, and 1. If they wanted points, you'd say negative 2, 0, negative 1, 0, and 1, 0. Okay? If they ask for the y-intercept, that's when you include that point. But don't include that point, just include where you hit the x-axis if they say roots, zeros, x-intercepts, or horizontal intercepts. So that is about horizontal intercepts. One more definition, and then we're done with vocab 2. Last one is about interval notation. It says in the definition page that interval notation is used for a portion of the real number line. Now you have the inequality. Let's talk about the notation or the interval notation you would use. A is greater than 0. That means don't include the A. It's going to go from A to infinity with parentheses. If you include the A, only thing that changes is the bracket. So you'll notice those two are very similar, except one has a bracket, one does not. These two kind of go together. Same thing, if you have an equal to, you'll notice there's a bracket. No equal to has a parenthesis. Follow number line order, least to greatest order. Now these are called the between ones, betweenness. So if we are between A and B, but we don't include them, use parentheses. If we do include both, put a bracket on both. If one is included and one is not, use the appropriate bracket or a parenthesis notation. All reals, you put negative infinity to positive infinity. Infinities always get a parenthesis because you can't land there. Okay. So then if we want to put the domain and range of this function into interval notation, the domain, this graph stretches to the left as far as we want, to the right as far as we want. We never lift our pencil. We never have to break the graph, so it goes from negative infinity to positive infinity. The range are the heights. The lowest point is 2. The highest goes up, up, up as high as I want. So I can include the 2 and I keep going up to infinity. Let's put these inequalities into interval notation. The interval for A is I am not going to include the 2, so I use a parenthesis, but I can have everything from 2 to 5, but I want to include the 5. Now B has 2 distinct pieces, so you should have 2 intervals with a union symbol between them. So we're going to go from negative infinity up to negative 2. I want to include it. I'm going to go from 4 to infinity, and the 4 I won't include, that's why I used a parenthesis to denote that open circle. And here, since I colored it and everything, I'm going to go from negative infinity to positive infinity. And then finally, let's put this in domain and range and interval notation. So one more practice. If we think about x's we have used from left to right, I sometimes will just go along the x-axis. Let's assume I've lined up everything on nice numbers, okay? Just to make it easier for ourselves. So I have an open circle here and a closed circle here. Close, open. So we have to account for all those things. So our domain, we had an open at negative 3, closed at negative 1. Then we jump to a new section that starts at 1 with a closed and ends at 3 with an open. Okay, let me say that again. Negative 3 to negative 1, open, closed, everything in between. closed at 1, open at 3. Now let's talk about range. The lowest value I see is -3, but it's open. I can have all the values up to a y value of -1. So I have open, -3, up to 1. The next y values I have are +1, all the way up to 2, and I have this little platform at 2. It doesn't matter if this one is open as long as somewhere else it's closed, which it is. So our ranges at that section go from 1 to 2. So that's a little bit about interval notation. So please at this time turn in vocab number 2 and work on IMath.